So today we're going to take another look at limits, and we're going to learn a strategy that is very useful and can help us out with much more complicated limits than we've dealt with before. Before we do this, though, we make sure that we understand the basic idea of limits, right? If we have 1 over infinity to any power, okay, it means it's always going to end up being equal to 0. Okay, and 1 over infinity is always equal to 0. If I divide by 0 from the positive side, I'm going to end up with positive infinity. If I divide by 0 from the negative side, I end up with negative infinity. Okay, and just to kind of briefly show you why, if I approach it from the negative side of 0, it's going down to negative infinity. Approaching from the positive side of 0 is going to go up to positive infinity. Okay, so those are the kind of basics. But we do still end up with lots of limits that are hard to deal with. Okay, so as sine x goes to 0, or sine x over x goes to 0, we kind of know that as an identity. But if we didn't know it as an identity, how could we evaluate something like this? Here's another one, x to the power x. We end up with 0 to the power 0. What's that going to be? Is that going to be 0 because the base is 0, or is it going to be equal to 1 because the power is 0? So there's kind of a competition between the base and the power here when you have 0 to the power 0. And it matters how we get to these forms. And these takes us to something called indeterminate forms. Basically, indeterminate forms are infinity over infinity or 0 over 0. Those are the main ones. And these ones, all these other ones, are essentially just variations of infinity over infinity or 0 over 0, or ones that we can put into those forms. Okay, because what we're going to use is something called lHopitals rule. It allows us to compare the ratio of two functions. Okay, the ratio in the numerator and ratio in the numerator compared to the denominator. That ratio will allow us to figure out these indeterminate forms and how we get to infinity over infinity or how we get to 0 over 0. And all these other forms essentially are just going to be put into either infinity over infinity or 0 over 0, and then we're going to apply this lHopitals rule. Okay, so one of the rules is we need to have the condition. Okay, if we apply lHopitals rule, if it's not infinity over infinity or 0 over 0, we get something that doesn't make any sense. Okay, so if we want to apply lHopitals rule to something like this with 1 over 0, well, that's not an indeterminate form. That's not 0 over 0. You're going to get weird results, okay? Because we don't have to worry. We don't need to do that because we can evaluate 1 over 0. We have an answer for that. We can actually work out the limit. Okay, so whenever you can work out the limit, we can't use lHopitals. Okay, so I'll give you an example. Here's 0 over 0. As I let x go to 0, I end up with e to the 0, which is 1, minus 1. So that's 0 on top, 0 on bottom. So first of all, we need to make sure we confirm that we have this indeterminate form 0 over 0. This is important. This is a condition we need to use before applying lHopitals. Now, lHopitals is fairly easy. The way it works is this. We're going to use a derivative, but we're not differentiating the quotient rule. We're just going to differentiate, find the derivative of the numerator function, and compare it to the derivative of the denominator function. And what lHopitals rule is going to say is that the ratio of these two functions, as it approaches the limit, is going to be equivalent to the ratio of their derivatives. Okay, so we have a function, let's say f of x up top, g of x on bottom. That ratio comparison, as we go to the limit 0, is going to be equivalent to f prime over g prime. Okay, so I'm going to maybe write it a little bit more explicitly. As x goes to a of f of x over g of x, we're going to say that's equivalent to the limit as x goes to a of f prime over g prime. Okay, we're differentiating the numerator and denominator independently of each other. Okay, so let's apply this and see if it works. Okay, so I'm going to do the limit as x goes to 0. I've got my condition at 0 over 0, and I'm going to differentiate the numerator. The derivative of the numerator is e to the 2x times 2 with chain rule. And notice I'm not using quotient rule here. I'm just using differentiating the numerator, and independently I'm going to differentiate the denominator. Well, the denominator or derivative x, the derivative of x is equal to 1. Okay, so now I've differentiated top and bottom. I'm going to say that this ratio of these derivatives is equivalent to the ratio of the original functions. And when I plug it in, okay, x is equal to 0, I end up with 2 over 1, or the limit is 2. Okay, so I'm going to go to the Desmos and just double check that. Is it really true that either 2x minus 1 over x as x goes 0 is actually equal to 2?